In 1913, Nikola Tesla was awarded a patent for his Tesla turbine. It takes advantage of the boundary layer effect, transforming fluid energy into mechanical power. We made a spin-off of this device based on a model by a YouTuber named Integza. We downloaded his Thingiverse files and proceeded to make a few modifications to the design. An updated steel shaft and acrylic discs were amongst the upgrades. For our project purposes, a tachometer to register RPM and a braking device to introduce a disturbance to the system for PID control were designed. Most of the parts were 3D printed, while the discs and turbine covers were lasered out of acrylic. Limited by supply air pressure and code parameters, this system easily hit and reached a steady state at 6,000 RPM under PID control. During manual testing, we were able to hit 10,000 RPM at 100 psi with no signs of mechanical instability.
To start off, we're going to talk from the sensor and work our way to the actual flow transmitter itself. So, starting with the encoder, we have 3 wired connections going to the Arduino Uno. The first two obviously just being power and ground wires. Signal wire going from pin 4 into the intermediate pin of the Arduino Uno, which can just be assigned at essentially any random port, which there are only 2 wires, one obviously just being a ground wire going to the input side of the PLC's ACOM, so that way it just has a common ground between both the Arduino and the PLC. And then the next part is actually a wire going specifically from, yet again, another input-output pin. In this particular case, Professor Sisk programmed it to be pin 5 for the output, so we'll output the encoder's value and it will be sent into a signal to ADV1. The flow transmitter uses current, so we have to use a separate module, an output module, which uses 4 to 20 milliamp signals to relay to the flow transmitter. Our common ground going from both the flow transmitter and the power supply ground. So we have a 3-wire connection there, sharing a common ground between the power supply's 24-volt ground, the flow transmitter's ground, and then the output module's ground. ADI1, and depending on the 4 to 20 milliamp signal that it obtains, the flow transmitter will either open or close to a certain degree based on that. And then
Hey, I'm Brandon and I'm going to cover the coding portion of the project. For the project, we used a click PLC that included a PID loop function. This allowed us to make sure that we could keep the motor at a set point and have it react to any disturbances. The PLC uses 70 different addresses when setting up a PID loop. These values are all stored and are either values or options that will affect how the PID works. The ladder logic was very simple. We only really needed 2 copy commands for our PID to work. Our Arduino would measure the RPM of the turbine and output a 0 to 5 volt signal to the PLC. Our first copy command would copy that signal to our raw process variable. From there, the raw process variable is run through the PID and becomes our process variable. The process variable is then compared to our set point to find the error, which will calculate our output percentage. Our second copy command copies our output percentage to our valve. The output will send a current between 4 to 20 milliamps to open the valve. From there, the PID should work on its own to keep RPM at a steady value after it has been tuned. For tuning, we found 5 for KP, 10 for KI, and 0 for KD at a 300 millisecond sample rate. With the auto-tuning function, the PLC found 11.5614 for KP and 2.75 for KI at a sample rate of 100 milliseconds.